Easy negatives teach slowly. Hard negatives are where better retrieval actually comes from. By the end, you'll be able to build a workflow like this, which mines hard negatives and trains embeddings to separate near misses and boost recall. I'm Professor Pi, teaching AI foundations with simple Python. Retrieval models rank documents for a query. The frustrating part is when the model ranks a wrong document just above the right one. That near miss is where real gains live. Hard negative mining finds those near misses and forces the model to learn finer distinctions. In practice, this matters for recommendation and search at moderate scale. For example, when you have a few thousand documents and need better top 1 recall. Conceptually, hard negative mining means look for the wrong answers your current model thinks are right, and then train on those. If the model already gets easy negatives right, pushing on easy cases gives diminishing returns. Mining focuses learning where the ranking boundary is slippery. We will build a tiny PyTorch workflow. First, we will compute cosine scores and spot a near miss. Then, we will train a tiny encoder with a simple margin loss on an easy negative. Show it barely moves the model. Mine a hard negative, then train on that. And finally, reevaluate the ranking. This keeps things concrete and lets you see the effect step by step. Now we compute initial similarities and show a near miss. This snippet computes cosine similarities in PyTorch to reveal a near miss where the wrong document barely wins. We first normalize both docs and the query using torch.nn.functional.normalize to make dot products behave like cosine similarity. The matrix multiply between normalized docs and the normalized query yields 1 similarity score per document. We then use torch.topk to get the 2 highest scoring documents and compute a margin gap between them. The variable sims holds the per document scores, while top stores their indices in descending order. A small positive gap indicates the model confuses 2 candidates. The printed top 1 and gap show a near miss that motivates hard negative mining. After seeing that small gap, you can picture why training only on random negatives would miss this specific error mode, and why we need a focused example to push the decision boundary. Next, we initialize a tiny encoder and measure an easy triplet loss. This example introduces a tiny PyTorch encoder F, built with torch.nn linear, and measures an easy triplet loss. We initialize F to the identity matrix, so the scores match the earlier cosine setup. The variable pos marks the correct document, and neg is a deliberately easy negative that is far from the query. We compute similarities by normalizing fdocs and fq and taking their dot products. Then form a margin-based loss with torch.relu so only violations contribute. The parameter m is the margin. Increasing it makes the model push positives and negatives farther apart, raising the loss. The printed easy loss shows a modest violation under an easy negative. This shows that the model separates easy negatives with little pressure. So training more on easy negatives will not fix the near miss we observed. Next, we mine a hard negative from the current model's predictions. This code mines a hard negative by picking the most similar incorrect document using PyTorch tensors. We reuse the encoder F to compute similarities sims3 between the query and all documents. Then build a list of negative indices in negs by excluding the positive. The argmax on sims3 negs returns the most confusing negatives position, which we map back to the original index hard idx. We then compute the margin triplet loss using torch.relu with this near miss negative, which is typically larger than the easy loss. A larger value means the model strongly violates the margin for that negative. The printed hard IDX and hard loss identify the culprit and quantify its difficulty. Finding that hard index is the core of the mining idea. The model itself points to its errors. Now we train the encoder specifically on that mined hard negative. This snippet performs hard negative training in PyTorch to reduce the violation on the mined near miss. We create an SGD optimizer and repeatedly forward the query, positive, and hard negative through the encoder F. Cosine similarities are computed by normalizing each vector with torch.nn.functional.normalize and summing element-wise products. The margin-based objective uses torch ReLU, so improvements only happen when the negative outranks the positive within the margin. The variable loss updates each step and backpropagates to move F, so the positive gets closer and the hard negative moves away. Larger LR speeds learning but risks instability. More steps improve fitting. The printed loss drop shows the hard triplet loss decreased after training, demonstrating targeted correction on the exact confusing example. Finally, we reevaluate ranking to confirm the positive moved up. This example evaluates the trained encoder by recomputing similarities and ranking documents in PyTorch. We normalize fdocs and fq again and use a matrix multiply to get one cosine score per document. The function torch.topk returns the two best candidates, and we compute their difference to get a clearer separation margin. If hard negative training worked, the correct document should rise and the gap should grow. A larger new gap signals sharper embedding geometry around important boundaries. The printed top one new and new gap show how ranking and margin changed after training, demonstrating improved nearest neighbor quality where it matters most. In short, the model now treats that near miss as a real training signal, not a forgotten edge case. Recap: hard negative mining finds the wrong answers your model thinks are right and uses them as training signals. Use it when easy negatives are already solved and you need better TopK recall. One caveat: mining can introduce noise if your encoder is unstable or your dataset is tiny. Next step: scale this exact approach by increasing your corpus size and adding an approximate nearest neighbor index so you can mine hard negatives across thousands or millions of candidates efficiently. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.